Hi, in this video, we're going to go through a step-by-step derivation of the duration and modified duration and see how does the modified duration work in the process of approximating the price change according to the change in the yield to maturity. Okay, so we'll first represent this on a graph. So we already know that the price of the bond is downward sloping with respect to the yield to maturity. So it's going to look like a downward sloping curve like this. Okay, so it's curved, not a straight line because it's a higher order polynomial. So remember the price formula for any bond, okay, is here. Just a reminder, right? So it's a higher order polynomial. So it's going to look like a curve like this, right? So let's say we have a bit of initial information here, which is the initial yield to maturity y0 and the initial price p0 here. Okay, so let's assume that the yield to maturity increases just a little bit, like the examples that we have given in previous videos. Okay, so let's assume that this is now our new yield to maturity. So it goes up here. All right, now the new yield to maturity will give us a new price, which is this this price here. Okay, right. So that will be our new price, and the price will decrease, of course, because the yield to maturity has increased. So the actual difference in the price would be this distance here. Okay, so basically, how do we get this distance is by calculating the prices twice using the original and the new yield to maturity, and then we can find the differences. This is something we have already done in the previous video as well. Okay, so how does the approximation how does it can be represented here? Okay, so we're actually taking the derivative at the original point here. Okay, so let's just try to write a tangent straight line here. So that's going to be the derivative of the price function at the original point here, right? So that's going to be tangent to the price curve here. Okay, so the approximation happens here. So if we zoom in a little bit, so we're actually using this as the approximation. So now we're saying this distance, okay, so this distance, let me just color it in a different way. This distance here is the approximate change, while this distance here is the actual change. So now you can see where the error comes from. Yeah, so this bit here, or this distance, this tiny distance, is going to be the error here. And this should be corresponding to the differences that we have shown in the previous examples, right? So as long as you can see here, the change in the yield is not too drastic, this could be a very good approximation, right? So for example, if it's too drastic, let me just change the yield to maturity over here, and the price would have changed by quite a lot. Okay, so if I still use the approximation here, the price would have been changed, or the approximation of the price would have changed even more. So the error here would be too great for us to use the approximation. So we don't use it when the yield to maturity changes by too much. Okay, so let's try to derive this step by step using mathematical tools, right? So just a little bit of reminder here, this has been given as a conclusion. Okay? These formulas are given as conclusions, right? So the price of any bonds can be calculated this way. We already know that. The Macaulay duration is defined this way, okay? And then the modified duration is the Macaulay duration divided by 1 plus y. And the approximate change in the price is hence the negative of modified duration multiplied by the price, the original price, of course, and then the change in the yield. Okay, so without looking at these, let's just try to crack this problem using pure mathematics. Okay, so if we want to approximate the change, we're basically getting this. So actually dp over dy, which is the derivative of the price here, okay, and then multiplied by delta y, right? So delta y is here, okay, and then if we multiply this thing by the derivative or the slope at here, okay, we basically get this point or this distance. So that's going to be our approximate change in the price. So we only need the dp over dy here. Okay, let's just do it step by step. Okay, so we know the price formula is going to be the summation of all the cash flow and then discount it. Okay, we're using yield to maturity here, so it's not r but y here. Okay, to the power of t. Okay, and then we're going to find the derivative of this thing with respect to y here. Okay, so it looks a bit daunting, but it's going to be quite simple if you just expand the summation operation. So let's do it step by step. So the first cash flow, CF1 here, divided by 1 plus y, and then the second one, CF2, let's just call it CF2, okay? So 1 plus y to the power of 2, and CF3, 1 plus y to the power of 3, all the way to this final payment, which is CFT, over 1 plus y to the power of t, okay? So it doesn't matter whether it's coupon or not, or how much is this coupon going to be, or what is the face value. Let's just call them cash flows, right? Let's just call them cash flows, right? So this whole thing is going to be our numerator, right? It's going to be our numerator. We're taking the derivative of this over dy, right? So this could be a little bit confusing at first, but let's just write it in the form of a multiplication, so with the negative exponentials here. So it's going to be this whole thing, okay, the CF1, 1 plus y to the power of negative 1, which is the same as here, as the fractions here, right? So, and then the CF2 multiplied by 1 plus y to the power of negative 2, and then all the way to CFT, 1 plus y, and to the power of negative t here, okay? And all of this, okay, dy with respect to y, okay? So in this case, it should be more obvious, or it's clearer that we're just going to take the derivative for each of those terms with respect to y. So 1 plus y is only a very basic linear combination of y, so it shouldn't change anything. Okay, so it shouldn't change anything. So let's just do it here. Okay, so we take the exponential down to the coefficient, and the exponential here should minus 1 as well. Okay, so here we have minus CF1, 1 plus y to the power of minus 2, and then minus, so be careful, this bit, minus 2 as well. So CF2, 1 plus y to the power of minus 3, and all the way to the last one, or should I write here as minus here, okay, minus t to the power of CF of t, 1 plus y to the power of here minus t plus 1. I should add 2 here, okay, in case we forgot here. Okay, so 2 over here because of the exponential here, minus 2, and then minus t here because of this exponential of minus t here, right? So still, it doesn't look like anything we have encountered, but we can simplify this. Since everything is in minus, we don't like the minuses or the division here. Let's just take the common factor out, which is the minus 1. Okay, let's do it step by step. Okay, so let's take all the minuses out. So it becomes the minus of CF1, 1 plus y, minus 2, and plus 2 times CF2, 1 plus y, and then minus 3, and all the way to the last payment, which is t times CFT, 1 plus y, and to the minus of t plus 1. Okay, so if it's t plus 1, you need a bracket up here. right? So that's t plus 1. Right, is there something else we can do? Yes, we can take another common factor out, which is the 1 plus y to the power of -1. So let's just take yet another common factor out of this, okay? And then we're left with the CF1, 1 plus y to the power of -1 plus 2 times CF2, 1 plus y, power of -2, and then the last payment, which is t times CFT, and 1 plus y to the power of -t here. Okay, so this should remind you of something, especially looking at the coefficients here, okay? Now, let's just reverse this into our normal looking fraction form, okay? So this is going to be minus 1 plus y, 1 over 1 plus y, multiplied by CF1, 1 plus y, divided by this, okay? And then CF2, 2 times, remember, 2 times CF2 plus 1 plus y to the power of 2 plus all the way to t times CFT divided by 1 plus y to the power of t. Okay? Right, now we almost have it because this thing really looks like our Macaulay duration, right? So our Macaulay duration is this. We're only missing the p here, and we're having this 1 over 1 plus y, 1 over 1 plus y, and the negative sign before this, okay? So we can multiply this thing by delta y to get to the approximate change, yeah? This is only derivative. We still need to multiply this by delta y, okay? So let's do it right here, which is going to be minus 1 plus y, okay? CF1 over 1 plus y plus 2 times CF2, 1 plus y to the power of 2, and all the way to t times CFT divided by 1 plus y to the power of t, okay? And then multiply by delta y here, all right? So to make this thing, okay, this conclusion here look like something we already know, we need one more adjustment, which is dividing p and multiplying p again. So we're doing the same thing twice, okay? So divide this whole thing just by p here, okay? And then we multiply p. So it shouldn't change the overall value of this. Now we can do something about it, okay? So notice that this part here, okay? This part here is exactly the Macaulay duration, right? So I'm just gonna color it in a different way. Okay, this part is the Macaulay duration, right? And then this Macaulay duration divided by 1 plus y, see? And what's that? That's exactly the modified duration here, okay? So added with this part, let me just use another color. Okay, if we add this part here, and that's going to be the minus of d star, which is the modified duration. So because of this minus sign here, right? And then what we're left with is the minus of d star multiplied by delta y multiplied by p itself. So we have it exactly here. Okay, so this is how we arrived at the approximation of the price change due to the change of yield to maturity. And why does the modified duration work this way? It's simply a linear approximation using the derivative of the price function at this point here, okay, at this point here. So we're using this straight line and the change in the straight line due to the change in yield to approximate the change of this curve, right? So there's bound to be some error, okay? There's bound to be some error, but as long as the change in yield to maturity is small enough, then it shouldn't be much of a problem. Okay, so it shouldn't be any problem here, right? So that's the step-by-step derivation. Okay, so most of the times you wouldn't be required to do that in an examination, but this should help you to understand why does the modified duration work. Okay, so if you're curious about, okay, so why does it work? This is how it works. Okay, this is why it will work, because it's simply the linear approximation at that point. Okay, or in some other ways you can say it's actually the first order Taylor series expansion. Okay, and that's the modified duration, and we can use it as the approximation for the price change. Okay, so for those of you who are interested in mathematics, you can expand it even more. Okay, and that does make sense in the world of finance, and that's called convexity, which we will talk about in some videos in the future. Okay, so by now you should be able to understand how does the modified duration work, and how does the Macaulay duration work, and why do we use it. Okay, so in the next video we're going to take a look at another function of using the modified duration here, which is called immunization. I'll see you there.